Okay, hello everyone. Today we're going to look at Phet simulations, and we're going to see how we can use this for um, learning physics, chemistry, biology, and other sciences. Right? It's a very good simulation tool which is available online. All you need to do is just search this Phet simulations. Go to this website, phet.colorado.edu. Right? Okay. Once you're here, today we're going to run some circuit based simulations for a current and electricity unit for IGCSE, right? So let's go to physics and then select our choices and get to electricity, magnets and circuits, right? Now it will refine the tools that are available. These are different simulations which you can use. These are presets, right? Uh, so let's begin with perhaps, yeah, I think let's go with this con circuit construction kit for DC power sources, right? Okay, let's click this, right? It has several variations. We're going to start with this, right? Uh, let it load. Once it's done, we are going to go to lab, right? Okay, here's the lab. Now over here you have all the things, the tools that you can use to test electrical circuitry, right? Uh, let's start with the bulb, right? Let's place a bulb. Now as you can see, there are two connectors. One is this terminal and this is the other terminal for the lamp. And first we're going to run this lamp and see what happens and in which direction the current does flow, right? So we're going to take a battery, we're going to take the wire, right, and we're going to just connect. It will automatically snap to the battery, right? Let's take another wire and connect it to the other terminal, right? Now since there is no switch, as soon as I connect this, it will start running, right? As you can see, the bulb is glowing, and over here I can use the voltmeter to see how much potential is there across the bulb or across this battery. Now at this moment this is 9 volts, right? uh, and as for the current, we need to see what is going through this conductor. Now the current testing device that this is actually used by the simulation is called the eddy current testing, right? You simply put a loop of wire around the current carrying conductor, and the electric field which is generated by these moving charges is detected in terms of the amount of current which is flowing through this conductor, right? Okay, there is another way that you can put the uh, our regular series type uh, ammeter, right? So we're gonna put our eddy current testing unit back. We're gonna break this circuitry. Now we want uh, the current to go through the ammeter, right? Now as you can see, we always say that the ammeters are supposed to be used in series, so there you have it, right? Okay, now we can also check the voltage across the board, and that's 9 volts, right? Now as you can see, these moving charges are the electrons, and this is what you call current. Current is actually the amount of charge flowing through a conductor in a specific amount of time, and that is measured in amperes. So if I just change this option, right, show current, I put it to conventional current, right? Now this is now showing you the direction of the conventional current, right, across the battery. Now remember, this is the positive terminal and this is the negative terminal of the battery, right? uh, let's turn it back to the electrons, the usual current that we use, and also it will tell you the values. Now this lamp is uh, having a resistance of 10 ohms, so that way if we just want to calculate the current using the formula V is equal to IR, right? Now over here This is the R and this is the supplied voltage, so we can also calculate the amount of current that will this bulb or this lamp will draw, right? Now let's look at the advanced options. At this moment, uh, the wires are offering very little resistance. Now see, as I move the slider, as you can see, the current is going down, the intensity of the light is also going down, and when it's too much, uh, the bulb is barely glowing, and you can see the speed at which these electrons were moving is now slower. That means less amount of charge is going through in specific amount of time, which means lesser current, since the resistance uh, of the bulb hasn't changed and the voltage hasn't changed. So consequently, uh, the current through this lamp will reduce due to the resistance of these wires, right? Now currently it's just the wires. Now there's also what we call as the internal resistance of a battery. Now if I increase that, you can see the same effect is happening, right? Now let's add real bulbs. Right, there you go. Now let's see what is the difference between a real bulb and an ideal bulb. The silver one is the ideal bulb. This is the real one. Now as you can see, uh, as I increase the resistance and less current is going through the bulb, consequently the resistance is coming down. Now this is what we say, that the Ohm's law is no more applicable in this case, the ideal case, right? In case of this bulb, no matter how much we increase the voltage or the current, the resistance will respond it will be directly proportional, right? If these are directly proportional, the slope will be the resistance, and that's a straight line in the graph. Now that's Ohm's law, right? But in real cases, that is not what is observed, right? So we're going to remove this real bulb, we're going to put it back, and we're going to use our regular bulb, right? Okay, now over here we're going to also discuss series and parallel combinations, right? We're going to put the voltmeter back as well. So to get a series system, we're going to need a switch so that we can see what is happening. We're going to break off this wire, connect it to the switch. Now as you can see, when the switch is open, the resistance is infinite. That means there is no voltage which can go through, or no current will flow through this switch. Why? Because the resistance is too high. Consequently, the current is going to be zero. As you can see right now, the current is zero. Oh, the bulb is turning. All right, there you go. Yeah, that's bulb number one, right? There we go. Let's take another bulb and let's connect them in series, right? There you go. The positive terminal is connected to the negative terminal of the bulb, and there we go. Okay, let's make actually a series of 3 bulbs over here to have a better clarity what will happen to the system. Let's take another wire. Let's move this bulb over here, right? This is second, and now let's add a third one. Yeah, okay. Once we have connected these, what we need to do is to connect this negative terminal, sorry, positive terminal to the main positive that is coming from the battery. Now this is what we call as a series combination of devices, right? I will call this as a series resistance combination. Why? Because these bulbs are actually acting as just resistance, right? Now I'm going to reduce the resistance to 0 for all 3 bulbs, right? And now I'm going to turn on the switch. As you can see, the current is going too fast. The battery is on fire because this nearly infinite amount of amperages that are going through. Why? because the resistance is not there. Now as soon as I give even a little value of resistance, uh, you can see that the current is now stabilized and the battery is no more on fire, and this is now operational. Now since there is no resistance, and as I told you that these light bulbs are resistance bulbs, right? So if they don't offer any resistance, they are not going to heat up the filament, and then there will be no light consequently, right? So I'm going to add some resistance. Now as you can see, uh, let's reduce it to zero point 0.9 animation speed limit reach. So just experiment and see what happens. I'm actually looking at this for the first time because I've experimented so many things, but I never did try to put it to 0 so far. So let's put it to 1 ohm for each bulb, and then let's see what happens in a series combination of bulbs. Right now, as you can see, these are connected in series. The power provided by the battery is 9 volts, and 3 amperes are being drawn since the resistance is 1 ohm. So the current will be the sum of all 3 resistances, right? It would be taken from the sum of 3 resistances. So using the equivalent resistance of these 3 bulbs, we will use this value of the voltage to find this current, and that would be 3. It would be 9 divided by this 3, giving you I being 3 amperes, right? Now we can check the voltages for each individual bulb. Let's say for the first one, the voltage is 3 volts. For the second, now across these 2 bulbs is 6 volts, and across, if I add up the 3 one, then the voltages are added to 9 volts. So each one of these bulbs is drawing 3 volts individually, and consequently the glow is very little, right? Let's just make this resistance go away, and now you can see these 2 bulbs are now drawing 9 volts, and each one is individually dividing the voltages in half, and hence they're glowing at the same intensity. But this one is not glowing because this is no more a resistance bulb. It's just a free connection, resistance free connection, right? And across the circuitry it's 9 volts. Across the single bulb it's 4.5 volts. Both of them will add up to 9 volts. So over here we can say that in terms of series combination of resistors, the voltages are added up to find the net voltage, right? In comparison to this, we'll see what will happen to parallel combination of these bulbs, right? So let's do some further experiments with this and see what happens. Now let's see if I just put let's blow some fuses first. I mean, no fun of doing science if you don't blow out stuff, you know. Okay, let's break off this connection, right? As soon as I break off the connection, you can see that the circuitry is dead. No more current is flowing. Current is stopped, and there you go. Right now, this is the current rating to which this fuse will work. Oh, as soon as I drop the current rating a little bit low, I mean, since the fuse was I need to replace the fuse. Okay, fuse replaced. Okay, this was actually happening to your devices at home as well. That most of the time, if your device goes offline due to some voltage or current variation, it's better to check the fuse first, right? This is a safety feature that electrical systems use in case if excessive current is drawn, so that the battery or your appliances don't catch fire due to over voltage or over current. These fuses are used with their specific limits, and once as you can see the current, I will now reduce. As you can see, oh, again, as soon as we dropped the resistance a little too low, the fuse went off because a lot more current was being drawn by the bulb due to less resistance, and hence our fuse just went off, right? Let's replace the fuse again. Okay, now this is a 1000 volt battery to experiment with. Now I'm not gonna do any experiments with this right now. I would highly encourage you guys to just explore this beautiful software. Appreciate the amount of simulations and the type of simulations it's offering, and do give it a check. You can enhance your workspace as well, and do a lot of things, right? You can use the symbol, or you can say uh, the blocks, right? Both of them are available, but I would rather use this to signify the importance of the intensity of light, right? So I'm going to put the voltmeter back, and I'm going to put the status battery back. That was 1000 volts, and let's see what will happen if we replace one bulb with a real one. Oh, oh God. Let me just, okay. Now it's all turned around. There you go. There you go. Okay, let's bring it down. Yeah. Now, as you can see, this real bulb is actually putting a lot of load on this battery. Even though the switch is not offering any resistance, the ammeter itself is designed in a way that does not offer any resistance. The fuse, let's remove the fuse to remove any ambiguities. Now, as you can see, the glow in the first two lamps is very low, but this real bulb is actually having more resistance, and it's drawing a lot more current. Let's see what is the potential across the real bulb, and that is 8.7 volts. So all of the voltage is consumed by this real bulb, and eventually these ideal bulbs are not receiving any potential. Now remember, potential is always from the positive terminal, so I will use the conventional current now to signify what is happening, right? As you can see, when the higher potential provides this conventional current, supposedly, the real bulb is consuming most of the voltages and delivering the remaining voltages to these ideal bulbs. And now both of these are sharing 0.93 voltages, because rest of it is consumed by this 8.07 volts are used by this real bulb, right? So over here you can see only 0.93 voltages are provided, and hence these are not able to glow much. As soon as I replace this with a ideal bulb again, and let's say, and now let's vary the resistance, right? Since the resistance is high, so it will consume more of the voltage and the current, and will allow lesser amount of current to go through this, and overall the net current, let's put another ammeter over here and see what is happening over here and between these two bulbs, right? So I'm gonna break this as well. I'm gonna take some ammeters. Oh, there we have it. Yeah, one. Let's connect this. Let's put another one. There you go. Now, as you can see, and the current, we need to add one over here as well, right? Okay. There you have it, right? Now, why I'm doing this is to show you that in series, the current does not vary. It's the total amount of current addition of all the resistances that are there in the circuitry that defines what is the amount of current being moving through the circuitry, right, through the wires. Now I'm going to use conventional current for the moment. Now I'm going to reduce the amount of resistance offered by the first bulb. As you can see, as I'm reducing it, the glow on the other two bulbs is increasing, the intensity is increasing, and as soon as I have the same value, all three of them will now share the amount of voltage. Now remember this is ideal case. This is not a realistic case. Even then, if I keep on increasing the intensity, resistance of the first bulb, now the other two bulbs are barely having any voltages provided to them. Right now I'm going to uh, put the voltmeter on this one. Now I'm going to use 3 voltmeters, right? There we go. The second is telling me the voltage across the second one, and oh, I can only use 2. All right. Uh, yeah, let's see the voltage across the big one, because these two are since of the same value, so they will have the similar behavior in the circuitry. Although the current is same in the circuitry, but the voltages are varying. As you can see, as I reduce the resistance, the voltage to the first bulb is reducing, and more voltage is now available to the other two bulbs, right? And their intensity is increasing, and the intensity of the first one is also normalized. And if I reduce the resistance to 0, not the first one doesn't glow because it has no resistance to offer, and the other two will now be at their full intensity at a resistance of 1 ohms, right? So do experiment with this. Do share your opinion. What other experiments you have done. Make a video, share your experience. I'll see if you have any questions. I'll be able to answer through your own video. Just put it in your channel or any playlist, and just share the link, and I'll hopefully respond back. Nonetheless, if you have any questions regarding this, please let me know, so that we may discuss things out, and get the better learning out of it, right? Thank you so much.